Hello, hello. So today we're doing 13.5 day 2, solving our trig equations, and today is the situation where some identities might start getting involved. So we're going to still solve the following. For the given range. Now, when it comes to working with these trig equations where there's a specific range involved where you're going to have identities, most of the time, the fact that you're going to use an identity is fairly apparent because you're either going to see the identity popping out of the equation or you're going to see an issue regarding the angles, or you look at it and there's no way to seem to get things alone. So just trust me, most of the time it's going to be fairly apparent. So you're going to see problems such as cosine of 2 theta plus cosine theta plus 1 is equal to 0. And this is going to be for all theta in degrees. So, I am wanting to solve this, which means I want to get things alone. But here's the issue. This is cosine of 2 theta. Cosine of 2 theta, anything other than just one angle showing up in the problem is, well, a problem. And I've got both theta and 2 theta showing up. And that's an indication generally that I'll need an identity anytime you see multiple angles in the problem. So we go to our identity sheet, and I'm looking at cosine of 2 theta. And cosine of 2 theta on the bottom of the back side has 3 different options of things that it can become. Which of these makes most sense depends upon the problem. Is the rest of the equation all sines? Do that one. Is the rest of the equation all cosines? Do that one. Is the rest of the equation a mixture of sines and cosines? Then you're going to have to pay attention to what's going on in the problem. Will one of these 3 identities get something to cancel out to where it's fewer trig ratios? Now, the problem we were looking at, everything was in cosines, so I'm going to use the second of my identities. So cosine of 2 theta becomes 2 cosine theta minus 1. Now you have to be careful when you are substituting a single term into a double term, which that's what we did here. One term became 2 things. The reason we have to be careful of that is if there was anything happening to the cosine of 2 theta, I need to remember parentheses because I have to do that to all parts of this. For example, if there was a 4 in front of here, then I would be putting this in parentheses and putting a 4 there so that it got distributed. Now, there wasn't a 4 there, so don't do that. But if there was, you have to be careful of that. If nothing's happening to the single term you replaced, then you're good. So, plus cosine of theta plus 1 equals 0. Now, after you have done this, we're going to start approaching... Ooh, I forgot my squared here. After you've done this, you're going to start approaching this problem the same way we did on Friday. There's just going to be one exception in the end. So, when I look at this, if it's hard to look at in cosines, you can switch it over to x's. You don't have to. Since they're all just regular cosines, it becomes 2x squared minus 1 plus x plus 1. The 1's will cancel out. I'll get 2x squared plus x equals 0. That's a quadratic equation. To solve it, I have to factor. Thankfully, this one I can just do greatest common factor. When you're factoring, it has to be equal to 0, which it was. And then you split these individually equal to 0. It's the zero product property. It's the reason it has to be equal to 0, because there's only one number in the world that if you see it and you know it's a product of two things, you know what you multiplied by, and that is 0. So x is 0, x is a negative 1/2. Now remember, it was never actually x, it was cosine. Cosine is equal to 0 at theta equal to 90 degrees and theta equal to 270 degrees. I just look at my unit circle, cosine's the x values. Cosine of theta equal to a negative 1/2 happens at 120 degrees and 240 degrees. Now, before I call this my solution, there's a couple of things I need to do, some of which we talked about on Friday, some of which are new. First off, are we in the right units? Yup. Are we in the correct range? Nope. So, for all theta, I add my 360 degree k, where k is an integer, to all of my answers. So this is the same stuff we did on Friday, but there's one more thing I need to check. When you start doing more complex solving, outside of basic things like adding and subtracting things to both sides, dividing by things on both sides, squaring things, square rooting things, I should say. Outside of those things, you have to start checking for extraneous solutions. Extraneous solutions, if you do not remember, is answers that you got in solving. Even though you did the correct solving process, they don't work in the original problem. This happens a lot when you start including identities. So we have to check this. If an angle works, its coterminals all work, so we only have to check our base ones that we got from the unit circle, and we plug them back into the original problem. So if I want to check theta equal to 90 degrees, my original problem said cosine of 2 theta, so 2 times 90, plus cosine of theta, cosine of 90, plus 1 equals 0. And both sides of my equation have to equal the same thing. In this case, since the right side's 0, they both have to be equal to 0. I just plug this into my calculator. Cosine 2 times 90, make sure that's in parentheses, plus cosine of 90 plus 1. It gives me 0. That one works. Therefore, this is a solution. And you just have to be careful to check all of them. Check theta equals 270. Cosine of 2 times 270 plus cosine of 270 plus 1 equals 0. Type it into my calculator. Yes, it's 0. No, you don't have to write out what I'm doing here at the bottom, writing the check. You just have to make sure you check them all. When I check 120, I get 0, and therefore 0 equals 0, which is what I want. When I check 240, I do the same thing. I've already checked them. You don't have to write out that you checked them, but if you tell me something is an answer that was an extraneous solution, it is wrong. So, do check your answers. Okay, sine of 2 theta equals cosine of theta. I notice my angles are not the same throughout the problem, so that is a problem. I look at my 2 theta, and on my identity sheet, 2 thetas are on the bottom of the back side. Sine of 2 theta becomes 2 sine theta, cosine theta. So that is what I'm working with. 2 sine theta cosine theta equal to cosine of theta. Now that it's all the same angle, if I want to change it to x's and y's, I can. I don't have to. Remember on these ones where you have both sine and cosine, you're better off getting them to the same side of the equal sign so you can factor. Get it equal to 0, factor out the y, 2x minus 1 equals 0, and split to solve. Y will be 0, 2x minus 1 will be 0, so x is positive 1/2. If you are the person who says, okay, I'm just going to divide cosine off of both sides, that's fine. Just remember, if you do it that way, you also have to check the case and where the thing you divided off, in this case cosine, you have to check that equal to 0, what that would give you. Okay, y was the cosine. So cosine of theta equals 0. That happens to be true at, now I'm working in radians, so pi over 2 and 3 pi over 2. Sine of theta equal to 1/2. Look at the unit circle. The y values are sine. 1/2 would be at pi over 6 and 5 pi over 6. Now I don't have to add any sort of k's because I didn't do for all angles in radians. If I did, remember, it's plus 2 pi k when working in radians. But now I need to check my answers. Now, in order to check my answers, remember, you're always plugging back into the very original one. But radians is not the mode our calculator tends to be in most of the time. So you have the option of switching your calculator over to radians and checking that way, or the radians versus the degrees isn't going to make a difference. If I want to check pi over 2 is 90 degrees. I would plug 90 into my theta in the calculator. I would check that, and I would check that it's equal to this. Remember, you plug in both sides separately. Sine of 2 times 90 is 0, and cosine of 90 is 0. Since it's 0 equals 0, you're good. The goal is to get both sides the same. It's not always 0. It's just that both sides of the equation are the exact same number. I will tell you right now, I've checked all of these. They do all work. Okay, next example. Sine of 2 theta equal to 1 for theta between 0 and 360. Now, the moment people see something other than regular theta, the instinct is to use the identities to switch it over. And if you do that, you get something along the lines of 2 sine theta cosine theta equal to 1. Now, in order to work with two different trig ratios in solving, generally speaking, you need to be able to factor it, which means you need it to be able to be equal to 0. But getting this equal to 0 makes this unfactorable, which is not helpful. So, sometimes, even if the angle is not just theta, it doesn't mean you can't solve it, because sometimes you're going to be in this situation where what you have is actually easier to solve in terms of, well, most commonly it's 2 theta. Here's why. Sine is alone right now. Sine is of 2 theta, but it is alone, which means I can start looking where sine is equal to 1. Sine is equal to 1 at 90 degrees. The only thing I have to pay attention to, though, is that by doing my sine inverse of both sides, that's technically what I'm doing when I'm asking what angle works, I'm left with 2 theta is equal to the 90 degrees. Divide by 2, and theta is 45. Except, there's one thing I have to keep an eye on here. If I'm going to solve a trig equation in reference to 2 theta, this range being in terms of theta is not good enough. I need the range to be for what works for 2 theta. So, since the angle is 2 theta times by 2. So 0 degrees is less than 2 theta, which is less than 720 degrees. I just doubled all 3 of those. 0 doubles just 0, hence it didn't look like it changed. So now I need all angles between 0 and 720. Now sine is 1 only at 90 degrees on the unit circle, but between 0 and 720, I can do coterminal. But when I do the coterminal, I have to do it to the 90 degrees. Because that's the one where I was saying sine is equal to 1. Not the 45. The 45 was my final answer. But I have to do the coterminal to the 90 and say that 2 theta could also be equal to 450 degrees. Divide by 2 and you get 225. So you do the coterminal to the version of the angle that you essentially did inverse trig on. And you're doing inverse trig when you're using your unit circle to say it's this angle. Okay. Got a few more examples. Oh, by the way, don't forget to check your answers. Yes, the previous 2 worked. Okay. Sine squared plus 2 cosine squared is equal to 4. The other time that you use your identities is when you look at the problem and you're like, I see an identity popping out. Now, it might not be perfectly the identity, but it can work out. For example, sine squared plus cosine squared screams to me. Now, this is 2 cosine squared, which I have to remember. Having 2 cosine squareds is like having a cosine squared plus another cosine squared. This is the identity, and I can change it over. Sine squared plus cosine squared is 1. By doing this, I've now made an equation that didn't look particularly pretty in the first place a lot easier. Subtract the 1 from both sides, I get cosine squared theta is equal to 3. To get rid of a squared, I take a square root, remembering that when I take a square root, I need a plus or a minus. So cosine is positive or negative 3. Square root of 3. Square root of 3 is bigger than 1. Therefore, this actually doesn't work out. You can try to do inverse trig. It doesn't work. But this one's technically no solution. If you prefer to do this, that's perfectly acceptable as a no solution symbol. Sorry about that. I hope that's not too loud. Okay. 2 more examples for you. And actually, I'm going to stop the recording right here. I'll mash together 2 recordings, but the bell's about to ring. Oh, not what I meant to do. So I just realized that I paused the video, honestly, probably at the perfect spot, because in hindsight, the problem that I just had written down, it doesn't make sense as a problem for me to go through while I'm gone. It's not a common enough solve. It's way more complex than what we need. So, yeah, we're going to skip over it. Clearly, I've done it, but yeah, no, we're going to move on. We're going to talk about some of the ones that are a little more common. So cosine squared theta plus 3 equals 4 minus sine squared theta. For theta between 0 and 360 degrees. So far as we've been going through the problems, when it comes to dealing with these ones that you're going to use an identity on, I've kind of told you, generally speaking, it's going to be one where the angle's going to be something different, like this 2 theta here, this 2 theta here. And so having 2 different angles in the problem creates a problem. And the other situation is when you're seeing things where the identity is coming out, where you're recognizing, and most commonly it's going to be actually those Pythagorean identities. So cosine squared theta plus 3 equals 4 minus sine squared. This is one of those situations where changing it to x's and y's is not going to get us something solvable. And that's another indication that you're probably going to need an identity involved. Because if changing x into x's and y's makes it impossible or nearly impossible, you've got a problem. So I see cosine squareds and sine squareds. I want them on the same side of this because of the fact that I have this identity here that says cosine squared plus sine squared is equal to 1. So I'm going to add. Oh, it helps if I don't try to write in an eraser. I'm going to add sine squared theta. Cosine squared theta plus sine squared theta plus 3 is equal to 4. That's my identity. 1 plus 3 equals 4 gives me 4 equals 4. My trig disappeared completely. So, this is a true statement at all times, though. 4 is always equal to 4, so my answer is all real numbers. Most specifically, 4 theta in between 0 degrees and 360 degrees, because that was the setup of the problem. Okay, I've got one final problem for you. This problem is actually going to be the problem that probably trips people up the most, at least without going extremely aggressive. This one's not as aggressive, but it's got a tripping point. Cosine is equal to 1 minus sine. Changing this to x's and y's doesn't work. Indication that I'm probably going to need an identity. But when I look at identities that involve sine and cosine, I'm limited. I've got tangent, if you're talking about sine divided by cosine, but they weren't getting divided, so not helpful. I can change sines into cosecants, cosines into secants, or I could go vice versa, but that's not helpful. I've got this one, but that requires squareds, not helpful. The cofunction identities, the negative angle identities, the sum identities, difference identities, half angle identities, double identities, all of them require angles being different, which could work if I had something where it fit the part where the angles were the same and it changed everything into being the different angle. For example, if I had cosine squared minus sine squared, I could change it to cosine of 2 theta and then work with that. But I don't have that here. Again, here, but they're getting multiplied. So, sometimes I'm going to have to manipulate the problem. This problem would be so much easier to work with. When I'm dealing with sine and cosine and ones, it'd be so much easier if things were squared. But here's the thing. It's an equation. I can square both sides. So I square this side, I get cosine squared. I square this side, I have to remember I'm squaring the entire thing all at once, so I put it in parentheses and square it. To square a binomial, I do not square the individual pieces. Sorry, I can't speak properly. My nose is just plugged up. It hates me. I know, TMI, but that's why my words sound weird. Okay, so I get 1 minus sine and 1 minus sine. But anyway, I was saying when you're squaring a binomial, you multiply it by itself. I think I forgot to finish the sentence. Okay, so I get cosine squared theta is equal to 1 minus sine of theta minus sine of theta plus sine squared of theta. Combine my like terms. Cosine squared theta equals 1 minus 2 sine of theta plus sine squared of theta. Now I'm seeing sine squareds and cosine squareds, which makes me happy, except if I try to put them on the same side, I get cosine squared minus sine squared, or vice versa. Now I do have an identity that says cosine squared minus sine squared. It's cosine of 2 theta. It's what I was actually just focusing in on, but I don't want to use that. Because if I were to use that, then all of a sudden I'm in a situation where I have a sine of a regular theta and a cosine of a 2 theta, which I want to get them to the same angle in order to solve. So that's not helpful. So instead, I'm going to focus still on the identity that puts sine and cosine together squareds. So off to the side, I'm just writing this off. This is my identity. I'm noticing I've got sines, and I've got cosines. But that cosine is squared. So the question is, can I replace cosine squared with sine squareds? And the answer is yes, because if I subtract sine squared from both sides, I get cosine squared theta is equal to 1 minus sine squared theta. So I can replace my cosine squared with 1 minus sine squared. I think I changed colors accidentally. Oops. Okay, now it's all the same trig ratio, so let's make it easy on ourselves. Let's switch it to x's. It's quadratic, and unfortunately, it's going to stay quadratic. But I want it equal to 0, so I do that. That cancels, 0 is equal to. That cancels. I'm also going to write it in order, so 2x squared minus 2x. I factor. I break apart. I remember that x actually replaced sine, so I'm looking for where sine of theta is equal to 0. What am I looking? Between 0 and 360, so theta is 0 degrees. Theta is 180 degrees. Theta is 360 degrees. Looking for where sine of theta is equal to 1, and I get 90 degrees. Before I call in my final answer, do not forget to check. All the way back to the beginning is what you're plugging into. Cosine of 0 might be equal to 1 minus sine of 0. Cosine of 0 is 1. Sine of 0 is 0. Yes, that one works. And here's the nice thing. If 0 works, 360 has to work, because they're coterminals. Okay, 180. Cosine of 180 equals 1 minus sine of 180. Cosine of 180 is negative 1. 1 minus 0 is 1. No, those are not the same. That one doesn't work. That's an extraneous solution. You have to indicate some way that that is not a solution. The easiest way to do it is cross it off. Sine of 90, that one works. And we're good. But don't forget to check for your extraneous solutions. Okay. I am done right there. Our homework assignment is on page 904. It is numbers 1 through 10, 13, 15 through 18, 20, 23 through 25, and 38. On this homework assignment, not all of them are complex like this. Not all of them require an identity. Remember that our test is on Thursday. You get to make a note card. Tomorrow and Wednesday are review days. Be amazing for the sum.